Hi, my name is Shahnamaz. Uh, in this lecture, we will discuss deformation, retracts, and homotopy type. So far we have seen one way of obtaining information about the fundamental group of a space X. Um, so if we have space X, one of the ways of obtaining information about it is fundamental group uh, is to study the covering space of X, and the other way involves the notion of homotopy type. So what it does, it provides a method for reducing the problem of computing the fundamental group of a space to that of computing the fundamental group of some other space. Now before we discuss deformation, retracts, and homotopy type, we have this lemma over here. So it states that, so let f and g be two maps from x to y, where x and y are given to be spaces. So here we have point y naught, so they are given to be continuous maps, where this x naught is some fixed point in x and y naught is some fixed point in y. So if h and k are homotopic, so if f and g are homotopic, so if f and g are homotopic, and if image of base point x of x naught remains fixed at y naught during the homotopy, so if the image of the base point x naught of x remains fixed, so it remains fixed at y naught during the homotopy, then the homomorphisms, then the induced homomorphisms, then the induced homomorphisms f star and g star, since they are given to be, so f is a continuous and g is a continuous map, so both these maps will induce homomorphisms f star and g star between the fundamental groups of x based at x naught and fundamental group of y based at y naught. So these two homomorphisms are equal. Let us prove this. So we had to prove. So we are given these two maps are homotopy. So there is a homotopy between these two maps. So since f and g are homotopic, there exists a homotopy say h from x cross the interval 0 1 to y, such that h of x0 is f of x, h of x1 is g of x for all x in x. also we are given that this point x naught over here, this remains fixed during the homotopy. So also we are given that h of x naught t, so this is equal to y naught for all t in the interval 0 1. So we are given that this h naught x naught remains fixed during this homotopy. Now what we have to prove? We have to prove the maps f star and g star are equal. So if we consider a loop, so let h be a loop in x based at x naught. To prove the homomorphisms f star and g star are equal, we will prove f star takes the homotopy class of h. I mean f star of homotopy class of h is same as g star of homotopy class of h. So to prove f star is same as g star, it suffices to prove f star of homotopy class of h, because this is an element of the fundamental group of x based at x naught. So this is same as g star of homotopy class of h. That is the homotopy class of f composite h is same as homotopy class of f composite g. In other words, it suffices to prove these two maps f composite h and f composite g are homotopy. So in other words, it suffices to prove f composite h is homotopic to g composite h. So this is what we have to prove. Now to prove these two maps are homotopic, we have to exhibit a homotopy between these two maps. So define f from 0 1 cross 0 1 to y by f is same as the composite map of composition of h with the map h times the identity map on the interval 0 1. So one can look out here. I mean, we have a map. So we have a map between the spaces 0 1 cross 0 1 to the map into the space x cross 0 1 and x cross 0 1 to y. We have the homotopy h, and this is the map. Since h is a loop based at x naught and x, so h is actually a map from interval 0 1 to x. So this 0 1 goes into x via the map h, and this 0 1 goes into 0 1 via the identity map. So this is the identity map 0 1. So that means this map over here from 0 1 to 0 1, from 0 1 cross 0 1 to y this is the map H composed with H cross identity map on 0 1. So what we do, we prove this F serves as a homotopy between the maps F composite H and G composite H. So note that F is a continuous map. So we have to prove these two maps are path homotopic. So this is a continuous map. Also, if we look at the function f of x0, it is h of h times identity of 0 1 of the point x0. So this is same as h of, so this h takes the point x to hx, and the identity map on 0 1 takes 0 to 0, but h of hx0 is same as, but h of x is same as f of x. So this is same as here, so this is same as f of h of x, which is f composite h of x. Also f of x1, so this is the map h of h times the identity map 0 1 base operated on x1. So this is the map, this is the map h of, so h takes x to hx, and this identity map on 0 1 takes 1 to 1. So this is like this. So this is same as G composite, because when we have 1 here, so when we have 1 here, we get G of x. So this is same as G of h of x. So this is G composite h of x. Now let us see what is going to happen at the base point. Also f of 0t is same as h of h cross identity on 0 1 of 0t. So this is same as h of, now h takes 0 to the base point x naught, because h is a loop based at point 0, and t goes to t, and h of x naught t is same as h of x naught t is same as f of x naught, but f of x naught is same as, since we know this homotopy fixes x naught to y naught throughout, so one can see over here this h carries this x naught to y naught throughout the interval 0 1. So this is actually y naught. Also f of 1t, this is h of h cross identity on 0 1 of 1t. So this is same as so h takes again 1 to 1 to x naught, because h is a loop based at x naught. So this is y naught. So that means these two maps are path homotopic. This map and this map is path homotopic. Hence these homotopy classes are equal, which proves that f star of h is g star of h. So this proves f star is same as g star. Now we have seen the homomorphism induced by the inclusion map. So if we have the inclusion map j from s1 to r2 - minus 0. So we have proved this earlier, that this map, the homomorphism induced by this map, which is a map between the fundamental group of S1 and the fundamental group of the punctured plane. So earlier we have proved that this map is injective. Now this map is not just injective, this is surjective as well. So more generally we have the following lemma. So this homomorphism is an isomorphism. Now we prove the same result in general case. So we have a lemma which states that the inclusion map J from the n-dimensional open ball, the n-dimensional ball to the space Rn plus 1 minus 0 induces an isomorphism J star between the fundamental groups of Sn and the fundamental group of the space Rn plus 1 minus 0. So let us prove this. So let us suppose, so let X be the space Rn plus 1 minus 0. And let B not be the point 1, 0, throw out a point in this space Sn. Now we can define a retraction. So define R from X to Sn by R of X is X over norm of X. So one can see over here this is a well defined function because X is non-zero. So we have the composite map. So therefore the composite map, so if I look at the map R composite J, which is a map from, so we have J a map from S1 to X, and R is a map from X, this is not 1, this is Sn, and R is a map from X to Sn. So it is like this. So here we have the J and we have the R, and so this is the composite map, which is R composite J. So this is a map from Sn to Sn. So this is an identity map because what it does, so this J takes an element, say this element X, small x, to X here because this is the inclusion map, and this X takes so this X goes to X by norm X, but norm X is a 1 because X was chosen in this space. So this is 1, so this is equal to X. So that means this X goes to X. So this map over here is the identity map. So therefore the composite map is an identity map. So if this is the identity map, hence the induced homomorphism will be injective. So it's an identity map. Note that R is given to be J is inclusion, and hence J is a continuous map. R is also a continuous map, so is there so is R composite J. So this is the identity map. Hence the induced homomorphism R composite J star, which is same as R star composite J star, is injective. Now this map being injective implies J star is injective. So hence J star is a monomorphism. I mean, it is an injective homomorphism. So this is what we proved earlier. This is trivial. Now to prove surjectivity of J star, we proceed as follows. So now consider the composite map now earlier we now consider the map J composite R. So earlier we took this map R composite J. Now we are taking the map J composite R, where R is a map from X to Sn, and from Sn to X we have the inclusion map J. So this is a map J composite R. So consider the map J composite R, which maps X to itself, which maps X to itself. So earlier we have seen this map is the identity map on Sn, but this is not the case here, because what we do, we take X, we take, so we have, suppose the plane, let us take for example n to be equal to 2, so n to be equal to 1, so we have this map R from R2 to S1, so S1 is a circle, and then we have again a plane. So what we do, we take some point here, then what we do, we take X over norm X, so we get a point on the circle S1, and this is the inclusion map. So this is a map from X to X, but what it does, it takes whole it takes all the point X and maps it to the elements of Sn, which are already present in this space, so which maps X to itself, but this map is not the identity map. So the map J composite R is not the identity map on X, but this is homotopic, but J composite R is homotopic to the identity on X. So we have not proved this yet, so for this we have to exhibit a homotopy. So indeed the linear homotopy H defined from X cross 0 1 to Y, sorry, to X given by So we take h of xt to be equal t of x, sorry, let us call this 1 minus t of x plus t times x by norm of x. So one can note here, so this, so indeed, I mean the linear homotopy given by this is a homotopy between the map identity on x and the map J composed R. So since the reason is that, so since h of x0 is x, which is identity on x of x for all x in x, also h of x1 is x over norm of x, which is a retract of x, which is same as J composite retract of x for all x in x. So x norm of x is same as a retract of x, and it is same as J composite R of x, because J of R of x is same as R of x, but this is in x. So this is an element of x, and this is an element of Sn. So that is why we don't write here R of x, we just write J of R of x, because this will make sense. Otherwise this will be an element of Sn if we write simply Rx here, but our homotopy is from x to x. So hence this is a homotopy. So also h of xt is no while 0. So why this is true? Because if we look at this map over here, this is same as 1 minus t plus x divided by norm of x, and we take x outside. Now this x is an element of x, which is same as Rn plus 1 minus 0. So this is x is no while 0. So for this element over here to be 0, this factor has to be 0. But one can look at this this factor over here. This factor over here lies between 1 and 1 by norm of 1, because if t is 0, this becomes 1. If t, so it is, sorry, this is not x here, this is t here. So if t is 0, this becomes 1, and if t is 1, this becomes 1 over norm of x. So since we can write here, so since this factor over here, since 1 minus t plus t over norm of x is a number between, so if t is 0, we get 1, and if t is 1, we get 1 over norm of x. So this number is always a definite number, because x is non-zero. So this number over here lies between these two numbers, which are both non-zero. So hence this factor over here is never 0, and this x is also given to be non-zero. So this means h of xt is never 0. So also let us look what is going to happen at b naught during the homotopy. So also h of b naught t. So h of b naught t is same as 1 minus t times b naught plus t of b naught divided by norm of b naught. but b naught is given to be the vector. B naught is given to be the vector over here. So this is the vector 1 0 0. So hence norm of b naught is 1. So if norm of b naught is 1, that means this will be equal to, so this quantity over here, this is 1, so this will be 1 minus t of b naught plus t of b naught, so that is b naught. So that means this h keeps the b naught fixed during the homotopy. So this is true for all t in the interval 0 1. Now we can invoke the previous lemma here. So since these two maps are homotopic, and this b naught remains fixed during the homotopy, then the homomorphisms induced by these two maps, they are going to be equal. So therefore, by previous lemma, therefore by previous lemma, it follows that the induced homomorphisms J composite R star and identity on X star are equal. But this map over here, this is bijective. So this means this map is bijective. So hence J composite R star, which is J star composite R star, is the identity map on the fundamental group of X based at point B naught. So this is the identity map, and hence, so if this is the identity map, so this map is bijective, which proves J star is surjective, and hence J star is surjective. Now one may wonder what made this proof work. So roughly speaking, it worked because we had a natural way of deforming the identity map on the space Rn plus 1 minus 0 to a map that is collapsed, that collapsed all of Rn minus 0 onto Sn. So that is what makes this proof work.